Can I get
Hey everybody, this is Anqui and Jatin Kataria. They want to talk to you about a monitor darkly. Give them a round. Come on. Congratulations for getting up here.
Vegas. Thank you. All right, we're going to get stuff shown on the monitors. And it's all going to work. All right. Okay, so this is work that we've done for the last 2 years in our spare time. So I wanted to tell you the story of how we did it and what we found over that time. So we have a big cast of characters. Okay, my name is Ang. Jatin is underneath this table. He will sometime reappear for this talk. We have a very strong Canadian named Francois, who we worked with, but he couldn't show up to this today. We have a person named Igor, which we'll talk about. We have a very concerned area man named Chris. And last but definitely not least, we have area man of concern named Shakib. And if you see his face on your monitor, things are really going to be bad. And he's actually in the audience today. So watch out. All right, so today's primary main objective is to go after these little devices that you connect to your computer that puts pixels up, right? Monitors. We all know what they are. Okay, and motivation for why we are interested in monitors. You know, a good hacker, right, is a lazy hacker. So if you think about this page, right, when you see this page, you think you're talking to your bank, right? The little green pixels on the left side here, right, makes you think this is an encrypted communication and you're safe. Now, think about all the resources and the research and the money we spent to create this infrastructure so that we can have this internet with SSL, right, that will show you these green pixels. You have to secure the browser, you have to secure the kernel, you have to secure the infrastructure for doing certificates and all this other stuff. I would say we probably cumulatively invested over $1 billion to make this infrastructure exist today the way it does. Okay, so let's look at the context in which we see this website. Okay, so we view it through this tiny little computer with a big screen on it that we call the monitor, right? So the lazy hacker would say, if I wanted to break the pixels that show me green, I could either break the security for that's built with $1 billion of investment, or whatever the security is inside this little monitor, right? And maybe it's not so great. And that's what we're here to talk about. Okay, so this whole thing started back in 2015 when Jatin and I got really sweet new monitors. Okay, so we bought these things and we said, wow, this is beautiful. And as soon as we plugged it in, we noticed this really curious thing, right? The USB device on it said, TUSB 3410 boot device, right? And the USB to I2C solution. So we looked at that and we said, oh, that's very interesting, right? So like a minute of Googling later, we found this really useful Dell forum response by Chris. So somebody asked, hey, I don't have a driver for this, T34, 3410 boot device. What is it for? Is it a problem? And Chris from Dell says, don't worry about it. That driver is only there for firmware updates, which we'll probably never do, right? But if you want the driver, here it is. And I looked at that and I said, how interesting, right? So Jatin and I started thinking, and I say, hey, Jatin, let's tear down this 34-inch monitor that we have lying around.
Well, we already have awesome monitors. Why don't we take that 34-inch, which is not doing anything?
Yeah, and then we're cool with this, but then Chris hears this, right, nearby, and he says, like, these monsters have no heart. Like, there's no end to their savagery. And I also have 1 million Vim plugins, and my life is sad, right? And we said, oh, this is really the saddest thing I've ever seen. So where are we going to find these monitors?
Why don't we go to the interns? They don't need monitors.
Yeah, we can.
They have like Dell 2410s sitting around doing nothing.
Yeah, we got a pit of interns. They get 24-inch monitors. They don't need them, right? So we started looking at the 2410s instead of the curved ones. And like 15 minutes of Googling later, we found this really nice document that describes a USB firmware upgrade instruction. Okay, and this instruction is just insultingly clear because the first instruction says the power goes into the power wall thing, right? And then the USB goes in the USB thing. But then, it talks about this U2410 ISP tool, in-service programmer, and then we started to get very interesting results, right? So we're seeing screenshots of this Dell utility that doesn't require any administrative privilege, that starts up a bunch of stuff, and at the end of the day, right, runs things like app test and a lot of other mystery, and just does the firmware upgrade for you. So we looked at the output of this program. We said, what is an app test? Like, what is this all about? We started Googling, right? We found a lot of documents mentioning Genesis and gprobe and all this other stuff. And we also found these documents from, the late 90s, early 2000s that had all these mystery hardware that updates firmware from these really old monitors. So if you see the one on the bottom, there's a parallel port with power supply going to VGA, right? And somehow this hardware changes firmware on monitors. So we start Googling more, right? We find mention of SD Micro, Innolux, Athena, and Dell. So we're trying to figure out what this is all about, okay? Like days and days of Googling later, we figured out roughly how this happened. So AppTest is a thing that's used by gprobe, which was created by a company named Genesis, and they were a big player in the on-screen display controller market, in the early 2000s, right? From that, we did a lot of Googling, and here's what happened, okay? So in 2002, Genesis created gprobe, and Genesis was, in 2008, later sold to SD Micro, and then SD Micro threw in some of their IP and created this chip called the STDP6000 something, right? That chip was then sourced to Innolux, which is partially owned by Foxconn, which is then something that's, the Innolux built a board that was eventually used in Dell monitors, right? So this is how, somebody wrote various insecure code in 2002 that caused, probably a few 100 million monitors in the world being vulnerable today. So that's, how it happened basically. And we were able to get a copy of gprobe, right? So this is a screenshot of what it looks like. The interesting thing to look at here is the software says we can connect to the monitor via things like serial, right, and also USB. And we're looking at things like the DDC to BI, right? So that's something that's important. We'll come back to later. So we got a copy of this firmware update tool, right? We ran it in a virtual machine. We dumped a lot of USB traffic, and we noticed that there are DDC packets embedded inside USB packets. Okay, so Jaden's going to talk a little bit about what DDC is.
So DDC is like a display data channel communication set up by VESA. So it is used by the host adapter to query the monitor about the hardware capabilities, what is the vendor, what resolution it supports, and blah, blah, blah. And then if you go to this, there are multiple versions of DDC which exist. There is DDC 2B, 2BI, AB, 2B+. And what we are working with here is 2BI, and which is a next version of 2B which works over I2C and talks to the host adapter. So here is what initiation of communication started with the host adapter to the monitor happens. It sends a SCSI command with the code CF, which is a generic vendor code, and it is wrapped over, it's wrapped in USB mass storage packet, which is sent over to USB. Then the USB request block contains a DDC2BI packet, which is an encapsulation over gprobe packet to do like different commands. So one of the commands, if you're looking here, is a run code command, which allows us to put PC anywhere in the monitor.
How convenient, right? And if we look into the gprobe documentation, right, all of the checksum algorithms are laid out for you. They're very simple. So again, we're taking messages that are supposed to go into I2C, packing it into USB, and sending it over to the monitor via the USB interface. Okay, so yeah, let me show you a really simple communication between the host and the monitor. So I'll play the monitor. Jaden will play the host, okay?
Monitor, initiating communication. Give me register read.
I, as the monitor, say, I acknowledge your request for initiation of communication.
I acknowledge your acknowledgement that you started, you wanted to do communication.
Okay, I have acknowledged that you have run the read register command, end of acknowledgement. Okay, but we're not done yet, right? This is just a send the command.
So this is like 6 packets to send a command. Hey monitor, let's do a communication again. Give me the response of my previous command.
I acknowledge your request for initiation of communication.
I acknowledge your acknowledgement that you want to do communication.
Okay, I have the result for you from read register, end of communication. Goodbye.
So 12 packets to get 2 bytes out of the monitor.
Right, but it works. That's how the monitor is doing it. Right, and this is the mechanism that the monitor uses to update the firmware from USB into the on-screen display controller. Okay, so we read some documentation. Let's void the warranty. Let's figure out what the hardware looks like. So we open up the back of the monitor. This is pretty typical, right? The top of the board is where all the power stuff is, and the digital stuff is on the bottom. Okay, and here's an architectural diagram, right? So you have the main SD Micro chip on the upper left-hand corner. Notice that that chip sits on an I2C bus, which is connected to a multiplexer chip, and that's the 4053, right? And that multiplexer, again, sits on a second I2C bus, which is connected to a USB controller, right, which is the thing that we're talking to. So traffic comes into this USB controller, goes onto the I2C bus, goes through this multiplexer, then eventually ends up directly on the I2C bus for the on-screen display controller. So we're able to send raw I2C packets through USB to this machine. Okay, and that's how things work. And we flipped the board over. This is pretty typical. We found an SPI flash chip that we were able to dump. So we dumped the code. And this is something we like to do. We like to do 2D visualization of entropy. So off the top of our heads, we looked at this thing and we said, I have no idea what that is. That looks pretty sweet, right? It's high entropy followed by low entropy. There's certainly pattern there. This stuff, somewhere in the middle probably looks like code. Stuff over here, maybe data, right? It's high entropy, right? I mean, it's low entropy, but it looks like there's some stuff in there that's interesting. And who knows? Maybe this is compressed data. We don't really know. And then we took it and we just ran string on this thing, and we're seeing a lot of stuff that we saw in the documentation. So there's app tests, right? Mentions of picture in picture, and things like OSD hide and OSD show, right? So this looks like we're on the right track. We want to play with these things. So then I said, obviously, let's throw this in IDA and see what happens, right? And this is what IDA did, right? And we looked at it and we said, oh, this is really hard. We can't figure out how to disassemble Turbo 186, which is the architecture here. So we started Googling around, and it seems like somebody on OpenRCE in 2008 probably did exactly this research, but maybe didn't tell anybody, because they're asking about exactly the same architecture in exactly the same format. And I think the binary is actually from one of these firmware updates. So we looked at this and we said, oh, we don't like x86. We're going to go do something more fun, right? And we put it down. We didn't work on it for like 6 months. And then 2016 comes along, right? And Jad and I are sitting around, and this is really bothering us. I have no idea how this works. Like, computers are hard. So we just write ILFAC an email, right? And in 6 hours or 8 hours, Igor responds and it says, like, here's a long, insightful explanation of how IDA works in Turbo 186, and also already disassemble this thing for you. Simple.
So this Mars Hex is basically a piece of handler run on the monitor to update the firmware on the device. And it was like a 200 kilobyte, I think 2 megabyte. And he reversed everything, and it was perfectly disassembled, and he gave it back to us. So we thought, like, we will do something like this with the firmware of the monitor.
Yeah, so I read his email and I said, I'm just going to do exactly what you did, right? And I got segment cited everywhere, and nothing worked out, and I failed. And then Jadon said, let's not do that.
Let's be monkeys and press space. So we added a hotkey, which if you add like space, or like it jumps to different references, you won't get a control flow analysis, but at least it will help you in analyzing things. So if OFAG is looking at it, please, sorry. So we have now, we can run code, but we want to do we want to run some kind of code on it, right? So we went through the gprobe documentation, and we found 3 commands. One is the register read, which helps us to read any registers, run code, placing PC anywhere we want, and RAM write, which allows us to patch shellcode into the memory. And there is no MMU, so you can execute anywhere you want. Okay. So we want. So there's a concept of app test, which is basically a unit test inside the monitor. So it creates a context, and it tears down the context and does something inside it.
Yeah, so now that we have this ability to write code into memory and then run code, right, we want to hijack something that seems like it might be useful to see if we can do a very simple hello world. So we found there's one function that says, OSD fill rectangle, right? That sounds like a good idea. We want to just put a rectangle on the screen to see if we can actually do this.
Let's patch it using RAM write.
Right, so Jadon wrote this thing, and it turned out to be the grossest code that we've seen to that point. It gets way worse than this, right? So this is what it looks like.
And I have looked at this for 3 weeks.
Yeah, and if you stare at this for hours and hours, it will make you want to puke.
It will get gross.
And Jadon definitely did stare at this for hours and hours. Okay, so now that we are able to dump some memory from the firmware, right, we're looking at the code with most of it disassembled, right? We noticed that the virtual memory address map is between this and this, okay? But there are all these far calls to this very mysterious memory region.
So we started, we thought like there is no reference to it, and we do not understand how to get this code. So we started dumping code. So we wrote a USB dumper, and so we took, there is a command which is listed called RAM read, but we were not able to make it work, although it works now. So we used reg read, which allowed us to dump 2 bytes at a time. So imagine like doing those 12 packet transfer to get 2 bytes out. So I wrote a memory dumper which allowed us to do 1 megabyte dump per 8 minutes.
Per 8 minutes. So you remember those 12 commands that you had to do, right? We're doing those USB commands for, what is it, 100 bytes at a time, right? So
Yeah.
this is what we did. We said, let's dump. Jordan writes the USB dumper. We dump, and we wait, and we dump, and we wait, and we dump. And it's very slow, right? And then Francois comes along and says, like, you guys dump too slow. Like, I'm going to totally do this differently. So he went off and he said, I'm just going to re-implement the UART using GPIO pins on the sock. That's going to be way faster. And we're like, no way that's going to work. 2 days later, he comes back and he says, UART implemented. Okay, he also hijacked standard in and standard out. So all of a sudden, we had a UART over GPIO pins on the monitor that not only allowed us to dump arbitrary memory, it also allowed us to hijack all these very important, very useful debug messages.
So it is very important to know that right now we were working with the assumption that there is only one microcontroller in that sock. But after dumping the F1000 range, we realized that it's actually a hardware abstraction layer to talk to another chip, another processor inside the sock, which is called OSD now, on-screen display, whose main function is to display images on the monitor. But the other OCM, which is on-chip microcontroller, is actually talking to other other components inside the sock and other external interfaces. So which is 8000 to 8000 is mapped to is OCM, and OSD has its own code running inside SRAM and its own kind of processor.
Yeah, so at this point, we know that we're now working with just one processor. There's at least 2 different processors inside the sock, right? And they communicate using some memory map register that we don't really understand yet. And we kind of hit a wall, so we spent like a million years Googling and clicking on pretty much everything that we're not supposed to, right, until we found this beautiful site, Doc88, which is a place where people upload, awesome proprietary documents for the internet and stuff. And you'd probably want to open this in a VM, but it did give us the exact data sheet for this chip that we're working with. And from there, we found pretty much everything we needed to know about how this chip worked. And we were right about this assumption that there is an OCM and an OSD chip or OSD processor, and they're completely separate, and they work more or less asynchronously from each other. Okay, so now that we have the data sheet, we've done all this stuff, let's try to display a picture, right? Let's get that to work. First, there are 3 things we have to solve, and if we solve these things, we got picture display, okay? We have to figure out where to transfer the image to the monitor, right? We have to figure out how to trigger the image display function to display that image we transferred. And then we also have to figure out what a color is, right? How the color is represented in this monitor.
So when you boot a Dell monitor, right, like if this image comes up. So the theory was that if we find this image, we will be able to find the code which loads this image, and our quest will be over. But we had a sober and professional,
very sober professional
discussion.
Yeah.
And after a few hours, we came up with our own analysis, and we both said that this is not a Dell image. So what is this on?
Well, I mean, so we looked at some part of the code, right? This clearly doesn't hold the Dell logo, right? But what about stuff like this on the left side, right? Like maybe that's some representation of image. What is the thing on the left, right? And if you stare at that for too long, it also does crazy things to your brain. Okay, so then Francois comes along, right? And
after a few days, he came up with me like multiple megabytes of data to stare at, and I looked at it for hours, and come on, that's obviously an OSD command packet.
Right. I mean, don't you see that? Obviously, right? This is just in memory at runtime, right? Just a big old blob of binary, and John stares at this thing, and he says, obviously, this is this structure.
So this OSD command packets allows the OSD to display packet anywhere in the screen. You can specify the coordinates, you can specify the size, you can specify the color, how many bits per pixel have to be used. And what we understood after a lot of reverse analysis of the IROM, which is the hardware abstraction layer, this is how it actually works. So you write the OSD packet inside the OCM virtual memory map, and then you engage a DMA engine to map this memory over to the SRAM of OSD. And as OSD is working asynchronously, it reads the packet and displays the image. And the similar way, you can transfer the image to the OSD using the DMA memory mapping. So this solved our first 2 questions, which was transfer and display image. Right, and the APIs which were used to do this was SDRAM read to check, verify our write, and the SDRAM write, which helped us to do all this. And this is what we came with. This is probably the most gross blinking, box blinking program I have ever written. And if you look at it for hours, I have definitely vomited once.
Hold on. Wait, you got to see it. You guys all have to watch this with us now. Wait, hold on. Why doesn't it?
So you will see.
No, it doesn't want to play. Hold on. No, no, you're not going to get.
Come up.
You're not off the hook. You got to watch this video.
Okay, so as you see that the block, I'm able to like move the box around anywhere on the screen. And
It's so nauseating. Ugh.
there was a blinky bug, which I figured out after recon.
All right, but this is after days of looking at this nonstop. So the last question we have to figure out, what is a color, right? I mean, is a 32-bit color? How is it represented? So we did the reasonable thing and filled a rectangle with rows and rows of colors, incremental value from 0, 1, 2, 3, 4, etc. So instead of getting very similar colors, we got these colors, right? So why is color 0 basically the same as color 2? Why is 1 totally different? Okay, and we didn't really know. Let's do some science. We take a tiny little microscope and we point it at specific pixels in order for us to figure out what color gets rendered into what pixel value. So we filled every rectangle with the value OX33, okay, and this is what we saw. So if you look at it, right, R is blank, G is 100%, and B is 100%, right? So this is individual pixel cells that we're looking at. And then we said, okay, let's do, instead of the same pattern, we do OX33, OX00, OX33, OX00. So, Jaden, how many bits does the monitor use to represent each color, each
It's
pixel?
obvious. So if you see 0 represents transparency and there are 2 pixels missing, so it's 4 bit per pixel.
Right, and then...
How do you encode colors with 4 bits, right? In normal RGB world, each component is represented using 8-bit, and there is an alpha component, so it represents a 32-bit color. So how do you do this now?
Yeah, so if you have 4 bits, then you can have 1 bit for R, 1 bit for B, et cetera, and that's clearly not what's happening here. So it turns out this monitor uses a thing called color lookup table, which is basically this index structure, right, that uses 4 bits to index into 32-bit colors. So this allows you to save space, right? You can have at most 16 different colors, but you can have colors that are 32-bit deep. So now the big question is, where's the lookup table? Can we change it? Can we modify it? And then we did a very, again, very sober, very collaborative work with Francois, right? And we did this for days and days to try to figure this out, where he dumped lots of memory and we helped a lot. And like 2 days later, okay, we finally find the structure that we think is the lookup table.
So it works in a similar way how we were transferring the images and the command package. So you generate a specific color lookup table structure, and you write it to the OCM memory map that memory region over to the SRAM of OSD. OSD picks it up and displays the color for that specific image.
Okay,
And
so we have everything we need. Okay, we're gonna display photo.
Images.
And we did it. Okay, so look at that. We have tiny little SSL logs. We have as many as we want, wherever we want, and that was sort of the point of this, right? But I looked at it and I said, we still have only 16 colors, and that SSL log actually had something like 26 colors. So that's not enough colors, Jaden. We gotta get more colors.
It is really hard. It has been really hard now.
Yeah.
So we went through some docs, and we figured out like the hardware does support at least 8-bit per pixel. So till recon we had only 4-bit per pixel, but now we have fixed up to get 256 colors, and the code is submitted into GitHub. But after going over more analysis of the documentation, the register documentation list we found a breakpoint, so which means that we can halt the monitor, figure out everything, and this is after like 90% of the research we have already done. And we have spent like weeks on it, even months, and now if we would have access to this breakpoint, we would have finished it in probably like 1.5 weeks or 2 weeks.
Yeah, so at this point, Jaden and I just kind of like put our hands up in there. I was like, oh, I can't believe we missed that one, right? That's terrible. So we said, like, interns, just go do the rest of it, right? Breakpoint everything, reverse it, tell us what it is. And Francois helped, so the interns went out, dumped the stack, dumped the heap, found pretty much everything we needed to do all the demos that I'll show you later. And then we find the treasure.
This was very surprising because the OSD should be allowed to display a pixel on the image, on the screen, but it is very surprising that it has the capability to read pixels anywhere on the screen. And what can you do with that now?
Yeah. We'll talk about that in a little bit. So we presented some of this research at Recon, and after the presentation, people who actually knew how monitors work came up to us and said, like, hey, stupid, you don't actually even need the USB cable because, there are I2C channels on DVI, HDMI, and VGA, etc. So we actually ported the code to run over the I2C interface, and now our demos do not require USB at all, although it can be done over both channels. And that stuff is on GitHub today. Now, let's have some fun with it, right? Let's make a monitor implant. So let's assume that we have a very simple base implant in the monitor, okay? And let's also assume that I'm a sneaky guy and I have control over a pixel, right? So if I blink the pixel, I should be able to transmit data to my base monitor implant, and I can do something very much similar to a command and control, right? So every time I sample a pixel, I can change the data, and I can do something like a command type, data, 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 which allows me to load arbitrary code, arbitrary data, execute code, and do all sorts of other things. Now, we take this pixel, we put it on the internet, right? And as we know, the internet is used for one thing, right? So we can put this pixel on photos of cats, right? We can do YouTube videos of cats. We can even do movies about cats. And once we do this, we can distribute this pixel down to millions and millions of monitors, and we can update them all at the same time, and we can have direct command and control down to those exact monitors. Okay? And within our organization, this is commonly known as cat-based world domination plan number 7. Okay? Now, so in the end, what do? Okay, we figured out that we can change whatever pixel on the screen whenever we want. We can also see every pixel on the screen, which is really cool. And for those folks who have followed our previous research, we even got Funtenna to work on the monitor as well. But that's its own conversation that we'll have later. So, enough talk, right? We're going to do some demos. Okay? And then first I have to figure out how this works. Huh? No, you got to... We swear there's an actual monitor underneath this table, and the demo is not rigged. But shooting a camera at the monitor is a little bit difficult. So, does it work?
I think you're...
Yep.
You have to go down and step. It is taped. It is taped.
All right, wait, there we go.
All right. Okay. So, I'm going to talk from beneath the table.
Yeah.
So first, I'm going to show you how to put random pictures on the screen, and you can not remove it. So so this is Shakib, as we talked about, and his picture is going to be on the monitor.
So this is a typical, the Ubuntu machine, no administrative privilege, and we're just showing, putting an image on the screen. Now, we didn't do this in GitHub, but we can actually make this permanent. So imagine if that happened to you, how terrible your life would be, right?
So my second attack will be, you all know about 4chan, right? And it is not, it doesn't have any TLS capabilities, but I'm going to give it to you.
We're going to secure 4chan for everybody.
We did.
So check it out, right? Can you move it a little bit if you can see that closely, right? So we get to put SSL locks wherever we want. And if we just line it up right, it'll be right on the browser where the SSL lock ought to be. So now 4chan has SSL, so yay.
The next attack will be if you guys know about HMI interfaces, where, in power plants and how an operator determine what has gone wrong in a power plant system or a nuclear fission system. So if you look at that green light, it tells that whatever gun barrel is perfectly working fine, but I'm going to change that to...
Right, so what if we were able to show the different status of the industrial control system just by changing the pixels that said this pump is good, this pump is bad? What if we were able to change the operator's behavior just by changing the pixels on the monitor? Right, we have a fundamental trust of, we trust that whatever pixel is coming out of the computer would be displayed on the monitor, and we're seeing that this is actually not even true. Okay, so the last one we're going to do is we're going to show the blinky pixel command and control thing that we talked about. So on the left side, right, we have a PayPal page or a PayPal account. I don't have any money in this PayPal account, which is really sad. Jaden's going to change that for me, right?
I'm going to put, how much money do you want?
Like $1 million.
Okay, let's do it.
$1 million.
All right, so I also gave it SSL protection, that phishing page.
Right,
and
there you
I
go.
put $1 million on it.
And the way this is working is there's a tiny little blinky pixel on the right screen that's communicating to the monitor, telling the monitor to put this image at this specific pixel value, and we can do this, of course, in real time.
But Ang, I don't want to give you $1 million. I want to change it now in
No.
real time. No, let me. So what we are doing is so let's suppose if we are going, we're gonna send a command and control packet from our server. Oops, is it even working? Sorry, my server has gone down. Why don't we talk about implication?
Okay, so anyway, that's the demo, right? And all the code that went into this demo is up on our GitHub.
Oh, it's up. It's up.
It's working. It's working.
Okay. Yep.
Yeah. Okay.
Oh. I don't know. It's not working. Okay, let's see. Now, yep, it's working now. Okay, so I'm gonna give you how much you want, whatever, to.
Now, yeah. Okay, so anyway, all the code that went into this demo is on GitHub already. The link is on. Okay, so let's talk about what this means, okay, implication-wise. You know, the first question is, you know, how big is this problem really, right? We looked at a single on-screen display implementation for one type of monitor. You know, we certainly found some vulnerabilities in it, but, you know, is this a pervasive thing? So to answer that question, we bought 4 other types of monitors that are very common. You know, they're on the budget end of things, 24-inch monitors that are approximately between $100 to $200. Okay, we looked at Samsung, Dell, Acer, HP. And what's inside these guys? These chips, these boards. The bad news is they're not SD micro. They don't run G-code or G-probe. The good news is this one is AmStar, that one is AmStar, this one is also AmStar, and so is this one, right? So it seems like AmStar is you know, very pervasive, very popular OSD controller that's used in the lower, the cheaper segment of the market. And it turns out this really cool dude named Alex Boglin already did all the work for us. So he figured out the way to do firmware updates to all the AmStar on-screen controllers. And this is actually a feature inside the Linux kernel now, right? So that's the link. This work has already been done. So it looks like the same type of vulnerability that's fundamental to the Dell monitor is also within, it's also inside all of these other AmStar monitors, which means, you know, we probably have made more than 1 billion monitors, right, so in the last 10 years. And most of those, it looks like, will be vulnerable to some type of attack like this. Okay, and the next question is, you know, how practical is this attack? I mean, you guys have to make up your own mind about it, right? But keep in mind that we don't have to have any privilege on the computer in order to launch this type of thing. So any unprivileged code execution will allow permanent, persistent firmware modification inside the monitor, right? And the last big question is, you know, how realistic is this fix? You know, because the way to fix this now, right, without a physical recall would be to have the vendor distribute a firmware update tool that patches some of these, you know, insecurities about firmware update and code execution, okay? But if they did that, they would also release exactly the algorithm and the protocol for updating all the firmware on all the monitors. So this is not exactly a simple thing to do. You know, this is something that I would like the community to talk about. You know, is monitor security important? I think it is. How do we actually secure the monitors that we have now, right? And how do we build more secure monitors in the future? So that's pretty much my presentation. And I have to say this, you know, we're from Rebel in Security. We do embedded security stuff when we're hiring. So if you want to do this type of research, get in touch with us. And also, big thanks to Connor Abbott, who did a lot of the demo code. Bob drew all this stuff that wasn't terrible. And Brian also helped a lot, and he's in the front row. So thank you very much. This is where the code is for all this work. Check it out.